So now we will talk about the banker's algorithm. So the name bankers is chosen because the algorithm could be used in a banking system to ensure that the bank never allocates its available cash in such a way that it could no longer satisfy the needs of all the customers. So whenever a process enters the system, it must declare or say maximum number of the instances of each resource type that it might need. So that means, say suppose you have a process P1 that has entered the system, and whenever it is entering the system, it has to first declare itself, or it has to say itself that, say to the operating system that I need two instance of the printer, I need one scanner, I need one CPU, something like this. It has to tell the maximum resource count what it needs for its execution. That means for its completing its execution. So your process, whenever it enters the system, it has to declare or say the maximum number of the instances of each resource type it needs for completing its execution. So this number should not exceed the total number of the resources in the system. That means, say suppose your system it has 5 printers, okay, 5 printer instances. So your process P1 assumption is the process P1 it enters the system. So as per Banker's algorithm, the process P1 has to declare the maximum need of the resources it needs. So say suppose the maximum your process P1 it says I need 10 instances of your printer. So this thing should not happen. Like, so available, the total number of the resource type you have is one, that is printer, and you have 5 instances of the printer. But your P1 is asking for 10 instances. Is it possible to give 10 instances of the printer to the process P1 whenever you have the total number as 5? No, right? So the process it has to make sure that it should not ask more than the total number of the available resources in the system. So when a process it requests a set of resources in the system it will check whether the allocation of these resources will leave the system into a safe state or the unsafe state. So if it not, like if the allocation of the resource to that particular process it leaves the system into unsafe state, then your operating system will not allocate those resources to the process, and your process it should wait until some other process it terminates, and that terminated process it releases the resources, right? So whenever you have those many number of resources, you can allocate or give those resources to the process that is waiting. So this Banker's algorithm it can be implemented using several data structures. So the data structures such as your here 1 minute, yeah, this one, the data structure such as your available, max, allocation, need. So these should be used. So we will now see what is available, max, what are these data structures. Okay, so let us consider we have n number of processes in the system. Okay, we have n number of process in the system, and m is the number of resource types in the system. So the first one available, so it means, so if we consider we have a vector of length m, that means that indicates the number of available resources in the system. So if available of j is equal to k, that means k instances of resource type rj are available. Okay, so available is nothing but how many resource type a system has, what is the availability of the resource types in the system. So we write available of j is equal to k, that means you have say suppose 5 instances of your resource type printer. So k it represents instances and j it represents the resource type. Okay, so available of j is equal to k means k instances of resource type j are available. Fine. Basically understand that available is nothing but the total number of resource types or resource instances of the resource types that are available in your system. Next is a maximum. Okay, so you have n cross m matrix, it defines the maximum demand of each process. So maximum is nothing but whenever a process enters the system, it has to declare how many maximum resource type it needs, right? So that is nothing but your max. Okay, so max is nothing but your the maximum need of a process, the demand of resource type from a process. So we write if max of ij is equal to k, then that means you have a process pi. Okay, this represents process, this represents resource type, and this is your instance. Okay, so if max of ij is equal to k, that means your process pi, it might or it may request k instances of the resource type rj. Okay, I represents any process, j represents any resource type, and k represents any instance. For example, there is a process p1, okay, and your resource is your printer, and you have 5 instances. In our case, what will happen? So we say that process p1, it might request 5 instances of this printer. Getting it? The third one is allocation. So an n cross m matrix, it defines the number of resources of each type currently allocated to each process. So this allocation is nothing but how many resources are currently allocated to a process. It gives you the allocation. Okay. So if allocation of ij is equal to k, that means your process pi currently having or currently has been allocated k instances of the resource type rj. Again, we'll consider I as p1, j as printer, and k as 5. So that means your process p1 has been allocated 5 instances of the printer. You have to read like this one. Okay. So the next one is need. Need means the remaining, resource, or how much still your process needs, or say suppose how many more resources type your process needs so that it can complete its execution. So we denote that as need of ij is equal to k. That means your process pi, it still needs k more instances of the resource type j. That is, I'll consider again p1 as I, and this is printer, and k is 5. So that means your process p1, it still needs 5 more instances of this printer to complete its execution. So need is nothing but maximum minus allocation. So say suppose your process P1, to complete its execution, it needs maximum of 10 resource type or 10 instances of the resource, but out of 10 only 5 are allocated to it, right? So that means your process, it still needs 5 more resources to complete its execution. So here P1 is your process 10. This is the maximum number of the resource it needs to complete its execution. So 10 is nothing but max. Okay, this one. Okay, then so out of 10, 5 are currently allocated to it. That means 5 out of 10 resource, it has currently been allocated 5 resources. So this 5 is nothing but your allocation. Okay, out of maximum 10 resource, it has been allocated 5 resource, but it still needs 5 more resource to complete its execution. How did we get this 5? So maximum minus allocation. Okay, 10 minus 5 is equal to 5, right? So maximum minus the allocation is equal to the need. Okay, so this need is nothing but your process P1, it still needs 5 more resource or instances to complete its execution. Fine. So these are the 4 data structures that are available in the banker's algorithm. So next, in the banker's algorithm only, we have again 2 types, that is 2 more algorithms. One is safety algorithm, another one is resource request algorithm. So first, we'll talk about the safety algorithm. Okay. So this is the algorithm. We have 4 steps here. So first, I'll explain this briefly. So first, work is equal to available. That means put all the available resource type into a variable called as work. So if your if your system contains say suppose 20 resources, okay, so all those number 20 would be allocated to this variable work, and finish of I is equal to false for I is equal to 0 1 till n minus 1. If suppose we consider there are n processes in the system, at the starting of the execution we will consider none of these processes are executed. That means I here it becomes 0 1 2 3 4 up to n minus 1. If we have 5 processes in the system, so n minus 1 would be 4. So that means finish of I would be false, finish of 0 would be false, 1 would be false, 2 3 and 4 would be false. Okay, then finish of I is equal to false. So we have assumed that none of the processes have been executed, right? So we'll consider the first process as not executed, it is false. Then we will check whether need of I is less than or equal to work. Now need means how much more your process needs the resource, whether that need of a process, whether it is less than or equal to the work is nothing but your total available resources in the system, right? So you have to check here whether how much more your process needs the resources, whether it is less than or equal to the available resources in the system. So if no such I exist, then go to step 4. That means we'll not consider this one here. Why? Because we have considered I as false. If all of the process have been executed, then we'll go here. Otherwise, we will go to the step 3. So we have considered that the process has not executed. That means it is false. So we will go here. Okay. So we'll consider this condition. Need of I less than or equal to work has been true. Okay, in that case what will happen is your work, or that work variable would be incremented. How you will increment is previous work value plus the allocation value. That means this work is nothing but the total available resources in the system plus how many resources have been allocated to the process. So that will be the number of, or the available number of the resources in the system would be updated. Then you'll check, or you'll what you'll do is like you have executed that process. Now that particular process will terminate. Okay, and then again you'll check for the next process. That means you'll come back to this step 2 and check for the next process which is there in the system. Okay, if all the processes have been executed, that means if finish of I is equal to true for all, then the system is in a safe state. The order of the execution of the process, we call it as a safe sequence. And if all the processes in the system has been executed without any deadlock and everything, then we say that the system is in a safe state. So we'll take an example and then we'll traverse through this algorithm and you'll understand it better. If this banker's algorithm is asked in your exam, then you just need to write this portion. That is, you have to tell what are the data structures available. So all these 4 you have to tell. Then you have to have this safety algorithm. Just write this algorithm. That's it. The next slide, whatever I am explaining, that is the example, you need not write that one. And after that, you have to again write resource request algorithm, not the example. Okay. So now I'll tell you the example, or we'll traverse this example for your safety algorithm. So say suppose, yeah, so we have 5 process in the system, that is P0, P1, P2, P3, P4. So available process in the system are 5. Okay, then we have this ABC is nothing but the resource types, okay, or the resource we'll consider. So we have altogether 3 resources in the system, A, B and C. Okay, so say suppose I'll write here the total available resource or the instances of resource type A are 10. Then the total available instances of resource type B is 5, and the total available instance of resource type C is 7. Okay, so we have 5 processes in the system, 3 resources that are in the system. But that 3 resource, how it is, that is like we have 10 instance of resource A, 5 instance of resource B and 7 instance of resource C. Okay, now this allocation is nothing but P0 or P0. Okay, this process has been currently allocated 0 instance of resource A, 1 instance of resource B, and 0 instance of resource C. Okay. Process P1 has been currently allocated 2 instance of resource A, 0 instance of resource B, and 0 instance of resource C. P2 has been currently allocated 3 instance of resource A, 0 instance of resource B, and 2 instance of resource C. P3 has been allocated, currently it is having 2 instance of resource A, one each instance of B and C. P4 currently has been allocated 0 instance of resource A and B and 2 instance of resource C. Fine. So out of 10, this is the allocation, current allocation. But what is the maximum need of these processes? So your P0, the maximum need of it is 7 instance of resource A, 5 instance of resource B, and 3 instance of resource C. So whenever this 753 it is given to your process P0, it can completely execute its task and it can terminate. So P1 likewise, P1 maximum need of P1 is 322. Okay, so 3 instance of resource A, 2 instance of resource B, and 2 instance of resource C. So whenever this 322 maximum capacity of that P1 has been allocated to the P1 resource, then it can complete its execution and it can terminate. Likewise for P2, P3 and P4. Then I'll talk about this available later. Then the need. Okay, so need is what is the full form, or sorry, what is the formula for need? Need is equal to maximum minus allocation, right? So now do this one. Maximum P0 it needs 753, but out of 753 only 010 are allocated to P0. Then how much more it needs? It still needs some resource to complete its execution, right? So that is nothing but your need. Need is equal to max minus allocation. So do 7 minus 0, that is 7, 5 minus 1 is 4, 3 minus 0 is 3. That means apart from your allocated resources 010, your process P0 it needs 743 resources to complete its execution. Whenever I see 743 resources, it doesn't mean 743 resources. It means 7 instance of resource A, 4 instance of resource B, and 3 instance of resource C. Okay, I'll tell again for P1. So P1 requires 322 resources. Out of 322, only 200 are allocated to it. It still needs this. You do just 322 minus 200. This 200. That means your process P1 it still needs 122 resources to complete its execution. Likewise for all these processes. Okay. Now I'll talk about the available. Okay. Currently, or basically, your system altogether has 10 10 instances of resource A, 5 instances of resource B, and 7 instances of resource C, right? But out of this 10, 5, and 7, so this is the allocation. This has been allocated already. Few instances of the resources have been allocated. Now check how many instances of the resources have been allocated. This column is for A, this is for B, and this is for C. Now calculate or do the total. 2 plus 3 plus 2. How much? 3, 4, 5, 6, 7. Okay. Then B, it is 1 plus 1, that is 2. C here 2 plus 1 plus 2, that is 5. Right? So that means out of this 10 instances of A, 5 instances of B, and 7 instances of C, you have already allocated 7 instances of A, 2 instances of B, and 5 instances of C. Just what you do is deduct this one from the available. 10 minus 7 is 3. 5 minus 2 is 3. Again 7 minus 5, here you have 2. Right? So currently available system or currently available instances of the resources A, B, C are 3, 3 and 2. Hope this is clear to you. Okay. Next, I'll talk about your safety algorithm. We'll traverse through the algorithm. Okay. So what was the first step? So first step was work is equal to available, right? Your work, I'll write here, work is equal to available. So this was in the first step, right? So this is nothing but how many available resources are there in the system that has been allocated to a variable work. Now what is the current allocation you have to check, not this one but the current available, not allocation, sorry, it is available. Okay, so current available is 332. That means your work now becomes 332. Okay, then we had in the step 1 only we had finish of I is equal to false, right? So finish of I is equal to false. That means we have 5 processes in the system, none of these are executed. Okay, I'll write something like this. I'll write here P0, P1, P2, P3 and P4. None of these are executed, that means all of these are false. Okay. Okay. So this is your first step in the safety algorithm. What was the second step? So you had finish of I is equal to one process, right? So now I'll consider the first process has not been executed. So I'll consider finish of I is equal to P naught. Then I'll check whether the need is less than or equal to work. Okay, we had this one, right? Need is less than or equal to work. I'll check this for process P naught. Okay. Okay. What is the need of process P naught? Here you have, right? That is 743 less than or equal to, what is work? Work is here 332, right? 332. Now check whether 743 is less than or equal to 332. Directly don't check, you check one by one. 7 is less than or equal to 3, 4 is less than or equal to 3, again 3 here less than or equal to 2. Okay, now this condition it is false, right? None of these are less than or equal to this number, so this is false. That means your process P naught, it cannot be executed and it has to wait. Okay, why? Because available resources, it needs 743 resource but we only have 3, 3 and 2. It cannot be executed, so P0 has to wait. Now I'll check for process P1 again in the step 2 itself. Now what is the need of your P1? It is 122, right? 122. Check whether it is less than or equal to work, that is 332. Okay, this is 3. Okay, now check 122 is less than 322. It is true, right? It is true. Okay, now whenever it is true, what you have to do? You have to calculate or update the work. So work is equal to work plus allocation. This is there in your algorithm. Okay, currently I am explaining this system. Fine, work is equal to work plus allocation. Previously what was our work? The value of the work 332, right? So 332 plus allocation of P1. What is allocation? Allocation is here. Allocation of P1 is 200. So 200. What is the total? The new value of work would be 322 plus 200, that becomes 532. Okay. So now P of I, that is our finish of I, that is P1, it will terminate. Why? Because this condition has become true and it has got all the resources for its execution. Now it terminates from the system and it gives back, whatever the resources it had. So this one. So previously it had 200 resources that has been added to this available, currently available. So right now whenever P1 terminates, you have 532 resources available in the system. So that means your finish of I becomes true, finish of 1 becomes true. So your this process P1 has been terminated successfully. Okay, I'll write T1. Okay, that one, the numbering is just for the sequence. Okay, next I'll check for the process P2 now. For the P2, check whether need is less than your work. What is need of P22? It is 600. Whether 600 is less than or equal to this new updated value of work is 532. Okay, 532. 600 less than or equal to 532? No, it is false. You cannot execute P2. Your P2 has to wait. Now check for P3. What is the need of P3? 011. Okay, 011 less than or equal to work is 532, right? This condition, what it becomes? It becomes true. That means your process P3 will terminate. Terminate in the sense you will give these resources, whatever the maximum resources it needs, you give to it and you make sure P3 executes. So if the condition is true, what you have to do? You have to calculate work, right? Work is equal to work plus allocation. What is the new value of work? This one. So 532 plus what is the allocated resources to the P3? It is 211 here, right? 211. What is the total here? So it is 743. Now this is the updated value of your work, remember, okay? So your process P3, it completes its execution. I'll write here. It terminates, okay? Now we have the process P4. Check for the need of process P4. That is 431 is less than or equal to, this is the updated value, okay? 743. You have to check this value only. 743. So it becomes again true. You have to calculate the work. Work is equal to work plus allocation. What is work here? 743 plus allocation of P4. What is allocated to P4? 002 here. So 002, that becomes your 745. Okay. So again your process P4, it terminates from the system. So I'll write this process, it has been terminated. Okay. This is the third process to be terminated from the system. But we still have P0 and P2, right? Those processes are waiting for your available resources. Now we'll again come back to P0. I'll write here. So now check the need of P0, whether it is less than or equal to your work. The need of P0 is 743, right? 743 less than or equal to, what is the new work here? It is here 745. So 745, this becomes true. Again you have to calculate the new work value. Work is equal to work plus allocation. So currently work is 745. The allocation of P0, that is this one, 010. Fine. Okay. How much you will get? You will get 7, 5 and 5. Correct? Your P0 has been executed or it terminates from the system. Then which is the last one? P2, right? So I'll write here P2 is equal to, you have to check whether need is less than or equal to work. What is the need of P2? It is 600 here, right? So check 600 is less than or equal to, this is the updated value of work 755. So it becomes true, right? So it becomes true. Now you have to check or calculate the new work value. Work is equal to work plus allocation. The current value of work is 755 plus the allocation of P2. What is the allocation of P2? 302, right? 302. How much you'll get? 7 plus 3 is 10. 5 plus 0 is 0. Sorry, 5 plus 0 is 5. This is 5, okay? And 5 plus 2 is 7. So your process P2 has been executed or it terminates. That means all the processes which are there in your system, those have been terminated successfully. Those have completed its execution. So that means your finish of I now becomes true. Okay. So whenever this finish of I becomes true, that means all the processes that are in the system are executed. Now check this. The last value, whatever you got, right, for the work 10, 5 and 7, whether it is same as the first value or the actual available resources that are in the system whenever, before starting this algorithm. So it was 10, 5 and 7. Again we have got 10, 5, 7. That means the resources have been, allocated properly to the process in one way or in one sequence, and that sequence has made the process to be in a safe sequence and the system to be in a safe state. Okay. Now how we have executed your process? So which was the first process to be executed here? So this terminated first, right? P1 terminated first. Then which terminated? This one T1, T2. P3 terminated next, right? P1, comma, P3, comma. Next terminated was P4. Okay, this is P4, comma P0. Then you have P2. Now the process is P1, P3, P4, P0 and P2. Whenever you execute the process in this sequence only, then they say that the system is in a safe state. It has not caused any deadlock. And this sequence we call it as a safe sequence. Okay. So this is regarding your safety algorithm in the banker's algorithm. Fine. That's it for today. We'll conclude our session. Thank you.